This video is going to be examples having to do with trigonometric ratios. And our essential question, how do you use trigonometric ratios to write and solve problems involving right triangles? We'll see a bunch of examples having to do with answering this essential question. So let's start out with a right triangle, ABC. We're given that angle B is the right angle. And we know two of the side lengths. What we're missing is the third side length. So before we can even begin talking about the trig function values, let's see if we can figure out the length of side BC. 10 has to be the hypotenuse, given its position across from opposite from the right angle. So if we call BC, if we call that x, so x squared plus 6 squared is going to equal 10 squared. We're using the Pythagorean theorem to solve for the missing side length. So x squared plus 36 is 100, which makes x squared 64. Well, 64 is a perfect square, so we now know that side length BC is 8. Okay, so side length BC is 8. We're going to take that, and now we're going to look at the trig ratios of angles A and angle C, the non-right angles. So if we first look at angle A, so here's angle A right here. If we are going to take a look at these three trig ratios, sine, cosine, and tangent, we're going to label the two sides that aren't labeled as the opposite and the adjacent side in relation to angle A. The opposite, of course, is across from A, so side BC, which has a length of 8, is our opposite, and then the side AB, which has a length of 6, is our adjacent. Side AB forms part of the angle A. So the sine of A, if we think SOHCAHTOA, the sine of A is going to be the opposite, 8 over the hypotenuse 10. 8/10, which reduces to 4/5. So we know the sine of A is 4/5. The cosine of A, so that sine of A is going to be down here, 4/5. The cosine of A is going to be the adjacent, 6 over the hypotenuse 10. So 6 over 10 is 3/5. So the cosine of A must be 3/5. And then lastly, the tangent of A is the opposite over the adjacent, so that's 8 over 6. 8 over 6 reduces to 4/3, so the tangent of A down here goes with 4/3. Okay, so that was everything with angle A. Let's see if we can give ourselves some space here, and we'll figure out what's going on with angle C. Well, our adjacent and our opposite are going to completely change. So with a new angle, angle C, the 6 now becomes our opposite, and 8 becomes our adjacent, because now our angle's position has changed. Opposite and adjacent have changed. 10 is still the hypotenuse, 10 is always the hypotenuse. So the sine of angle C is the opposite, 6 over the hypotenuse. So that's 6/10. We've seen before is 3/5. So the sine of C is also 3/5. The cosine of C, the adjacent over the hypotenuse, gets us 8/10, which is 4/5. So you can see in a right triangle, the sine and the cosine of the two angles actually are shared. So 4/5 right here. You can see the sine of A is the cosine of C, and the cosine of A is the sine of C. And then lastly, the tangent of C is the opposite, 6 over the adjacent. 6 over 8 is 3/4. So the tangent of C 3/4. How about a new triangle? We're looking for the sine of angle A. Sine is the opposite over the hypotenuse, 12/13. Answer choice A. How about the cosine of A in this triangle? In order to figure out the cosine of A, we need the adjacent side, which is right here, the adjacent over the hypotenuse. So we don't know the length of the adjacent side, but we do know, if we call it x, we do know, because of the Pythagorean theorem, x squared plus 12 squared should equal our hypotenuse, 13 squared. So x squared plus 144 equals 169. So x squared is 25, which is a perfect square, so x must be 5. That gives us our adjacent, 5 over our hypotenuse, 13. Answer choice C. Okay, same triangle, so don't go through all the work of figuring this side length out. We know this is 5. We don't need to do that all over again. So now the tangent of A is the opposite over the adjacent, 12/5. Okay. If you know the sine of theta is 5/13, let's see if we can't figure out cosine and tangent. So let's start by drawing a triangle and labeling the sides, knowing that the sine of theta is 5/13. That actually gives us side lengths. That tells us that if we pick an angle to be theta in our triangle down here, here's theta, 5 is the opposite, so here's 5, and 13 is the hypotenuse based on the sine side length ratios. So we have 5 and 13. We've done a number of examples where 5, 12 are the legs and 13 is the hypotenuse, so we know the other leg is 12. 5, 12, 13. So with that being said, having drawn our triangle, then the cosine of theta is easy, 12/13. The tangent of theta, 5/12, once we know the side lengths. Solving a triangle involves finding all side lengths and angle measurements that aren't already given in the problem. So what we want to first focus on is solving for x. Knowing that the angle opposite x is 23, right here, knowing that angle and knowing 52 is the adjacent side, x being the opposite side, tangent is the correct trig function to use because tangent is the trig function that takes the opposite and the adjacent as the ratio. So the tangent of angle that is 23 degrees is equal to x over 52. So that's why we choose tangent. Now that's really just a ratio, a proportion, a ratio equal to a ratio. So we can cross multiply and figure out the tangent of 23 degrees in our calculator. And once we do that, here's 23 degrees, don't forget that degrees, tangent of 23 degrees in the calculator, we cross multiply, x is equal to 52 times the tangent of 23 degrees, which is 22.1. Now to solve for y, why not take into account the ratio that involves the hypotenuse and the adjacent? Well, here's your angle 23. We know the adjacent, we know the hypotenuse. Cosine is the trig function to do that. That's the adjacent over the hypotenuse. Again, set up a proportion, cross multiply. This is a little bit more challenging than the previous problem because we're going to cross multiply here and we're going to get y times the cosine of 23 degrees equal to 52. That's going to require us to divide do one more step, and that's to divide the cosine of 23 degrees on both sides. It cancels here. So y is equal to 52 divided by the cosine of 23 degrees. Once that's in your calculator, you should get 56.5. So we've got our three side lengths. Here are our three side lengths: 52, 22.1 for x, 56.5 for y. We know this angle is 23 degrees. We know this angle is 90 degrees. It's the right angle. We still don't have theta. So how do we get theta? Well, obviously in a triangle, 180 degrees is the sum of all the angles. If we subtract 90 and 23, we'll get theta, and that's going to solve our triangle. We have all side lengths, we have all angle measurements. Okay, x is the hypotenuse. What trig function are we going to use in order to solve for the hypotenuse when we know the adjacent side to an angle that's 52 degrees? The cosine of an angle is the adjacent over hypotenuse. So we know 52 degrees is the angle. We know 20 is the adjacent. What we don't know is the hypotenuse, x. So set up a proportion, cross multiply. X is going to equal 20 over the cosine of 52 degrees. Plug it in, and we get 32.5. Okay, similar problem here. Only now we're solving for y, so let's see. We figured out x in the previous problem. 52 is the degrees of the angle we know. We've got the adjacent side 20. Y is the opposite side. So how about which trig function helps us deal with adjacent and opposite? Well, that's the tangent. Tangent of an angle is the opposite over adjacent. So tangent of 52 degrees is the opposite side y over the adjacent side 20. Set up a proportion, cross multiply. 20 times the tangent of 52 degrees is our y, and that is equal to 25.6. Solve for side AB, and that is our adjacent side when we know angle 72, angle A there 72. So we know the hypotenuse, we don't know the adjacent. Cosine is going to be our trig function of choice, so the cosine of 72 degrees is our adjacent side, we'll say AB, over our hypotenuse, which is 52. So cross multiply. 52 times the cosine of 72 degrees is the answer for AB. Okay, now how do we solve for an angle if we don't know either of the two non-right angles in a right triangle? Well, we're going to write a trig ratio in terms of theta and the two unknown lengths, or the two known lengths rather. That's going to give us a value for the trig function. So in this case, if we're solving for angle A is, sine of A is the opposite, 38 over the hypotenuse, 48. We can do the inverse sine on both sides of the equation. That's going to undo the sine of A and leave us with just the angle A on the left side. The inverse sine of 38 over 48 is going to be a value that will be the angle measurement of angle A, 52.3 degrees in this case. And you can plug that inverse sine right into your calculator. So how about solving for C? We're going to do the inverse cosine, since we know the adjacent in the hypotenuse, and that inverse cosine is about 37.7 degrees. Now we're approximating those angles, so they might not add up to 180 exactly. We might be a tenth or a thousandth off because we're rounding those angle measurements. But let's solve for alpha here in this example. Alpha here, we know our adjacent side, and we know our opposite side. So labeling your sides is going to help. The trig function with that goes with the opposite and the adjacent is the tangent. So the tangent of alpha is the opposite over the adjacent. So now what we want to do is we want to take the inverse tangent on both sides of the equation. The inverse tangent of 32 over 34 is going to be our angle measurement for alpha, which is 43.3, answer choice B. How about beta in this case? Beta is here. We know the hypotenuse of the triangle is opposite the 90 degrees. We know 15 is our adjacent. So the trig function we want is the cosine. So the cosine of beta is the adjacent over the hypotenuse. Right? Beta is the inverse cosine of 15 over 30, which is also 1/2. But beta, that is, gives us 60 degrees. Okay, back to solving for side lengths. We've got our angle measurement 72. We want BC, which is our opposite side length, and 52 is our hypotenuse. So the sine function, sine of 72 degrees, is going to give us our opposite side, BC, over our hypotenuse, 52. Set up that proportion. 52 times the sine of 72 degrees is our missing side length, BC. Plug it in and we get 49.5. Okay, how about PQ? Now we're solving for the hypotenuse. PQ is the hypotenuse. 11 degrees here, angle Q. That means 33.5 is our adjacent side. So adjacent and hypotenuse, that's going to be our cosine. So cosine of 11 degrees is adjacent 33.5 over hypotenuse PQ. Again, set up the proportion, cross multiply. PQ is going to end up being 33.5 divided by the cosine of 11 degrees. Plugging it in gets us our final answer for side length PQ, 34.1. Okay, how about solving for another angle measurement C? Angle C here, let's call that alpha. Here's alpha. We know the hypotenuse length and we know the adjacent side is 20. So that means we're going to start out with the cosine of alpha. We know the cosine of alpha is 20 over 55. So alpha will be the inverse cosine of this ratio 20/55. Plug that in, final answer 68.7 degrees. Okay, we can use right triangles to set up problems involving shadows. For instance, we've got a building. So here's a building. We've got a point 340 feet away from the base of the building. So here's the bottom, here's the ground. Let's pick a point right here. This distance we're calling 340 feet. And from that point, the top of the building forms an angle of elevation of 65 degrees. How high is the building? So what we're really after is this height of the building, x. Well, you can see we've drawn ourselves a right triangle, and we can use a trig function in order to solve for this height of the building. So what we've got is an angle 65 degrees here. We've got an adjacent side length, and we're trying to find the opposite side length. So tangent is the trig function for the job. Tangent of 65 degrees is the opposite over the adjacent. Cross multiplying 340 times the tangent of 65 degrees is the height of the building. So when we plug that in, 729 feet. while flying a kite on 100 feet of string, you notice that the angle of elevation of the kite is 62 degrees. How high is the kite? All right, so here's, let's draw ourselves a kite. Right, here it is. We've got 100 feet of string. So there's our 100 feet of string. And you notice that the angle of elevation of the kite, so here's our horizontal line, the angle of elevation of the kite, 62 degrees. Okay, how high is the kite? Well, now what we want, again, just like in the previous building example, we want the height of this kite. The given information now is our angle 62 degrees, but now we also know the hypotenuse, and we want to find the opposite. So the sine function is what we want in this case. The sine of 62 degrees is the opposite, x over our hypotenuse, 100. Proportion, cross multiply, 100 times the sine of 62 degrees is the height of the kite. So we're flying our kite at a height of 88.3 feet. Okay, similar to the buildings problem, we want to know the elevation of the sun when we know how tall a person is and how long their shadow is. So let's see if we can't do a quick sketch. We've got our lovely person here who looks much taller than 5.5 feet, but let's just call this person 5.5 feet. We've got the sun. All right, here's our sun. We're getting really artistic on this one. Here's our sun. Okay, the sun is shining its rays down on this person so that the person is casting a shadow. Here's the person's shadow right here. Okay, there's the person's shadow, 8.25 feet long. And of course, this person is 5.5 feet tall. All right, and of course, the person is standing completely straight upright so that they form a 90-degree angle. What we want is to figure out what is the angle of elevation of the sun, which we'll call alpha. So we're figuring out an angle alpha. We know its adjacent side. We know its opposite side. So that's going to be a job for the tangent function, tangent of alpha, opposite over adjacent. The inverse tangent is what we're going to use on the ratio of 5.5 over 8.25. When we plug that into the calculator, we get 33.7 degrees.